Welcome to This Explainer. Today we're diving right into Chapter 28, Magnetic Fields, and we are going to uncover the invisible rules that guide the matter of our universe. We're not just looking at basic physics here, we are looking at the fundamental architecture of reality. We're decoding the forces that govern everything from the glowing auroras in our atmosphere right down to the permanent magnet holding a grocery list to your refrigerator.
So, let's start with a really simple mystery. How do you measure a force you literally can't see? Physicists obviously don't have some magical magnifying glass for magnetism. Instead, they have to throw charged particles at it. It's kind of like throwing paint at an invisible man. We have to read the high-tech digital data those particles leave behind. It's through the motion of these charged particles that the magnetic field reveals its shape, its strength, and its incredibly strict rules of engagement.
Here is our roadmap for today. We'll be hitting 1. Defining the magnetic field. 2. Uncovering the electron. 3. The Hall effect explained. 4. Tracing particle trajectories. 5. Cyclotrons and synchrotrons. And wrapping up with 6. Forces on wires and dipoles.
Let's jump right into Section 1, Defining the Magnetic Field.
To really understand this invisible hand, we have to look at its mathematical engine, the magnetic force equation. The magnitude of the magnetic force, that's F subscript B, is proportional to 3 things: a particle's charge, Q, its speed, V, and the magnetic field itself, B. But notice that multiplication symbol in the middle. It's a vector cross product. That means the geometry of exactly how a particle enters the field dictates absolutely everything about the force it's going to experience. And this right here perfectly illustrates the key difference between electric and magnetic forces. See, an electric field will push on a charged particle whether it is sitting perfectly still or flying by. But the magnetic force, it acts only on moving charges. If you hold up your right hand to visualize this cross product, fingers pointing with velocity, curling to the magnetic field, your thumb points to the resulting force. Because this magnetic force is always exactly perpendicular to the particle's velocity, it literally can never do work to speed a particle up or slow it down. It can only steer its direction. It is the ultimate invisible steering wheel.
Moving on to Section 2, Uncovering the Electron.
So, back in 1897, J.J. Thomson set up this beautifully ingenious experiment using a cathode ray tube. He fires a beam of unknown, glowing particles through a vacuum. First, he applies an electric field, which pushes the particles in one direction. Then, he applies a magnetic field exactly perpendicular to the electric field, creating what we call crossed fields. By carefully tuning the magnetic field until its steering force perfectly canceled out the electric push, the beam traveled dead straight. This precise balancing act allowed Thomson to calculate the particles' velocity and, ultimately, their mass-to-charge ratio. He figured out that the particles lighting up his screen were over 1,000 times lighter than hydrogen. And that exact moment, he hit the nail on the head and discovered the electron.
All right, Section 3, The Hall effect explained. So what happens when electrons aren't flying through empty space, but are instead drifting inside a solid piece of copper wire? Well, in 1879, a 24-year-old grad student named Edwin Hall proved that the exact same magnetic deflecting force applies. When you place a current-carrying wire in a magnetic field, the drifting electrons are steered sideways, basically creating a tiny traffic jam of negative charge on one edge of the wire. This leaves a positive charge on the other side, establishing a transverse electric field right there inside the solid wire. Once the electric force pushes back hard enough to balance the magnetic steer, we hit equilibrium. We can actually measure this voltage, the Hall potential difference, and use it to determine the exact density of charge carriers in any material. Today, this exact principle is what powers the sensors inside your smartphone, your car's anti-lock brakes, and even fluid flow meters.
Let's look at Section 4, Tracing Particle Trajectories. This is where the right-hand rule becomes visually mesmerizing. Inside a liquid hydrogen bubble chamber, an invisible gamma ray has just transformed into an electron and a positron. Now, the positron is the antimatter twin of the electron, meaning it has the exact same mass but a positive charge. Because they have opposite charges, the magnetic field filling the chamber curls their neon-lit trajectories in completely opposite directions. The spiral shape happens because the particles are slowly bleeding off energy as they bump into liquid hydrogen atoms, but the magnetic field relentlessly just keeps curling them inward. But what happens if a particle doesn't lose its energy? Well, because the magnetic force is always perpendicular to velocity, it acts as a perfect centripetal force. It locks these circulating electrons into a beautiful, glowing, uniform circular orbit. The radius of this circle is mathematically locked in by the particle's mass and speed divided by its charge and the magnetic field strength. It's an absolutely stunning visual confirmation of the physics equations we discussed earlier, literally painted in glowing light.
Moving to Section 5, cyclotrons and synchrotrons.
To study matter at its absolute deepest level, you have to smash particles together at incredibly high energies. But you can't just build a straight-line accelerator thousands of miles long. Instead, physicists invented the cyclotron in the 1930s. By using a magnetic field to continuously steer protons in a circle, they could repeatedly loop the particles back through a small electric accelerating gap. With each lap, the particles gain speed and rapidly spiral outward. But there was a catch. As particles get closer to the speed of light, relativistic effects cause them to fall out of sync with the electric pushes. To solve this, the synchrotron was born. In a synchrotron, both the magnetic field strength and the oscillator frequency are constantly varied or synced to keep the particles on a single massive circular track no matter how ridiculously close to the speed of light they get.
To give you a sense of the sheer scale we are talking about here, generating a 500 giga-electron-volt proton inside a 1.5 Tesla magnetic field requires a synchrotron ring with a radius of 1.1 kilometers. That's enough to encircle an entire neighborhood. It's a machine the size of a small city, entirely dedicated to manipulating microscopic specks of matter using the exact same cross-product math we saw earlier.
Finally, Section 6, forces on wires and dipoles.
So the absolutely crucial point to remember is that while a magnetic field only pushes on individual moving charges, those forces add up. Because drifting electrons cannot escape sideways out of a conductive wire, the microscopic magnetic force acting on billions of them simultaneously transmits a massive physical force to the wire itself. If you bend that wire into a loop, the opposing magnetic forces on either side create a twisting motion, a torque. This torque on current loops is the whole shebang behind every electric motor on Earth, industrial scrap metal lifters, and even the intense electrical breakdown you see around highly charged copper wires. The microscopic becomes macroscopic.
But hey, what about magnets that don't have a power cord? Ultimately, the permanent magnets holding up notes on your refrigerator exist because electrons themselves possess intrinsic magnetic fields. In quantum physics, this is defined by a property called spin, creating a magnetic dipole moment. Every single electron is essentially a tiny quantum bar magnet. In most materials, these microscopic magnets point in random directions and just cancel each other out. But in ferromagnetic materials like iron, they align, turning a mundane piece of metal into a permanent source of that invisible steering force.
The physics we've explored today perfectly describes how these forces shape our technology, our industries, and our understanding of the cosmos. We can calculate the orbits, we can build the synchrotrons and harness the motors. But here's the wild part. The fundamental reason why electric charge even exists in the first place, and why it is intrinsically linked to this invisible, space-bending magnetic hand, that remains one of the grandest unsolved mysteries in science. It's a humbling reminder that no matter how elegantly our math describes the how, the universe still keeps a few secrets about the why. Thanks for joining me for this explainer today. Keep questioning, keep looking closer, and I'll catch you in the next one.